is enabling FPGA process methods from Dajung. Sorry. She's a PhD student supervised by Ryan Kastner and is on the computer science and engineering from the University of California, San Diego. Her research interests are embedded visions, embedded systems, and high-level synthesis. And yeah, I'll start with your talk.
Okay. Hello, my name is Dajung. I'm so glad to give our talk about our recent research work enabling FPGAs for the masses. This project is with by Generic, but he cannot make it because of some issues, so I'm gonna present instead of him. So there are so many applications in various domains that have the potential to use FPGAs for their target systems or already have used them. The problem is that even though the experts in these area are very skillful and experienced, hardware design is very challenging for them. Even for me, I'm a hardware engineer, it's very challenging. And the efforts of hardware engineers, a lot of efforts of hardware engineers in recent, it seems like high-level synthesis tools can make it easy for many application designers. But from a lot of our experience in many different application projects and many other researches, its high-level synthesis tool is still the area of hardware experts, and they have still the difficulty gap between them, the application domain and hardware domain. Let's see the example. This is a generalized software code of convolution operation in the computer vision application domain. It's very intuitive, and many software application engineers would program like this. However, when we try to implement this one in the HS tools for FPGA design, it doesn't give a good result. If I program the convolution code as a hardware engineer, I will use a line buffer and sliding window over that. And this, my program would be like this. This HS program describes the hardware operation line by line, and maybe software programmers doesn't like this kind of program, but I'm pretty sure this is very efficient in HS tool, in the HS implementation. And our synthesis results prove that the restructured codes in the right side is pretty much better than software version C code. This results means that the HS programming should be totally different from software programming. I've shown that the HS program should be how different HS program is from from software programs using the kernel convolution kernel example. Convolution kernel is one example of regular programs. Currently, many compiler methods, such as polyhedral model, is used to many compiler methods, such as polyhedral model, is used to implement the efficient hardware HS program. One of the research example is Joel In's FPGA 13 in last year. They tried to use the polyhedral transformation to generate efficient HS program. However, polyhedral model is not working well for the irregular programs. Irregular programs has the indirect memory access or unbounded loop, and some irregular programs fail to optimize it in HS tools, like using the HS optimization program. Let's see the example of irregular programs, because when we compare the synthesis results of irregular program, it's gonna be worse than regular programs, as we've seen in previous slides. This is the example for irregular program Hoffman tree creation, which is used for the Hoffman encoding. This figure describes the basic structure of Hoffman tree creation. It gets the input. That's sorted list, and it takes the first two elements in the two elements with minimum frequency and generates intermediate nodes. And this node will be added to the list using a heap, and it goes continuously in this way. However, this pseudocode is a software version of describing Hoffman tree creation. If we try to implement this FPGA design with this input code in HS tools, it may not work, because in last parts it has unbounded while loop, and it hinders to use this HS program, like HS optimization program. So we can conclude that it is absolutely needed to rewrite the code to create an efficient hardware architecture. So we changed code like this. Instead of using heap in software program, we put one more VRAM to store intermediate data. And this can help by adding the one more VRAM buffer. We can change the code like this with fully bounded loop, and now these two while loops can be pipelined. So when we compare the result of two different results from both versions of code, the restructured codes in HS programming style is pretty much dominant over software programs. We have these kind of results from many different applications, and we can meet their target performance using HS programming in a short design time. However, all these results are based on our hardware experiences, so it'll be a little bit difficult for software programmers to achieve these results, good results. So HS tools can give a good quality of results as a manual design, but it absolutely needs the restructure the code in a little bit different style from software version, and that requires domain knowledge as well as hardware design skill. We would like to fill this difficult gap between two different domains. So we combine domain-specific language and hardware synthesis, high-level synthesis. There are several challenges to achieve that, like generating restructured codes for module-level optimization and designing a large complex systems by connecting these small modules, or building an end-to-end system for final results. We would like to suggest this formalized tool flow from application code to building FPGA design chip. So I will explain a little more detail about these challenges and show our solution, our suggesting solution. First one, for generating rich structured code, we built domain-specific language high-level synthesis template. Let me show the example. In computer vision domain, there are so many applications such as face detection, edge detection, or line detection. These applications share some common kernels, and even more, these kernels operates in some specific computing patterns. So in this way, we can narrow down many applications into several HS templates, which will give the optimized hardware design. We can generalize this to other application domains such as computer vision, linear algebra, or machine learning, something like that. So all these application domains has a similar hierarchy in this triangular structure. And with defined DSL HS templates, the DSL compiler can give a restructured code which will be running the HS tools and generate efficient FPGA design. This is the example for the overall flow. The canyon detection is very popular algorithm in computer vision area. It has many steps like this. And one of the steps, the second one, use a software filter. And luckily, the other three modules are working in the similar way of computing. So this pattern is defined in our HS templates library. So we can reuse this kind of computing pattern for other modules. Simply, canyon edge detection has 4 main kernels, and these kernels are already defined in our HS templates. So all we have to do implement canyon detection system are using these templates and connecting them. This pragma is for that, so making connection between the modules. We will say it as a parent description. Parent description is how different kernels can communicate with each other and exchange the data. This pattern description is inspired by the common parallel programming patterns, which is already known to software programmers a lot. So, using this DSL HS templates and using this parent description, again, this parent description is for communicating between the modules. Our DSL compiler can generate restructured code like IP cores, and in final part, HS tools can implement FPGA design for finer results. And we think it is necessary to test our IP cores. The IP cores generated from our tool flow. So in a real, it should be done in real chip. So, however, the current HS tools does not support the automatic integration with IP cores and host PC. So we would like to suggest that integrate with our tool flow with a well-defined communication protocol API such as RIFA to connect host's computer. In this way, we think we can expand FPGA uses into the more broader users like software programming as software programmers. So if writing code is given, then HS tools can generate an efficient hardware. However, generating efficient programming with HS tools is a little bit difficult. It requires domain knowledge as well as hardware knowledge. So we would like to fill the gap between the domain between them. So we define the several challenges for that and suggest a solution like this. Domain-specific HS templates for generating restructured code, and parallel programming patterns for designing a large, complex application systems. And for final design, we will suggest integrating RIFA with our tool flow for building an end-to-end system. We believe that in this way, we can expand the FPGA uses to more broader computing society. Thank you.
So we have time for a few questions.
Do you support or anticipate this library approach also for systems which have a hardware and a software part?
We have worked on these things and we have a small prototype for this, and we expect that it can work on, we can do all these flow things. The chip.
Yeah, so what I meant is, I see a lot of heterogeneous systems coming up, where we have a program, an application, where we don't want to build everything in our FPGA and our hardware. But we rather want to have some kind of joint system, where, for example, part is done on the CPU and then offloaded to the FPGA. You've seen this also in all the talks during the day, in the morning. And I think this library approach can also be extended throughout this interface, so that the library brings you a kind of function which has an HLS part and kind of a software part. But this is not anticipated or discussed in any way by you.
We are currently focusing on the FPGA uses for the software programmers, and after doing that, I think we can expand to some other systems like, as you said, heterogeneous system. This work is about the HS tools, but our other other students in our group working on that parts too. So we are expecting the whole work for the larger systems.
So I see your target linear algebra here, and what I see that we have a lot of highly optimized C libraries for linear algebra, and what they are all doing is once you give them a matrix and a vector, they are not running one algorithm, but they first analyze your matrix, they look is it sparse or not, they try to optimize it, and they try to block it maybe, and then once they have this pre-processing, they do very like the algorithmic kernels you have spoken of. They do a simple dense matrix vector multiplication on this specific block and so on. And I think for an efficient hardware implementation we need to do something similar. So once we also need to maybe have this flexibility in different kernels which are depending on the data, and this data pre-processing can be done on maybe not on the FPGA but on the CPU.
What is the point of your question?
How could this be? So your goal was to build an efficient library for these different domains. And what I see is in the CPU world we have not one single kernel but many different kernels. Mm-hmm. And you now say, okay, we have one kernel, one template for it, and that's it. How does that fit together?
Yeah, she didn't say anything about which linear algebra kernels you have.
Okay.
You can also have many of them.
So you have to select one.
The same thing as in software, I would say.
In software you don't select one, that's my point.
Maybe you can discuss it.
Okay.
So, one more question? Yeah.
The domain-specific language, when you showed it, it kind of looked like C. It looked like C with some pragmas around it. So is that the case? The domain-specific language kind of looks like C, and the DSL compiler sort of expands that out into a restructured C that.
Well, we are working on there is a, well, as I said, there is a prototype of this thing, and the main author, Nervig, is working on that with the Python one.
Okay.
And this is about our research directions for the future.
Sure.
So we can expand all these things with the C or the other languages. So that's our current position.
Right.
Okay, thanks, speaker. Okay.